Wave-particle duality. Wave-particle duality is one of the most fundamental and intriguing concepts in quantum mechanics. It reveals the dual nature of matter and light, showing that both exhibit characteristics of both waves and particles depending on the context in which they are observed. This duality challenged the classical understanding of physics and became a cornerstone in the development of quantum theory. The concept of wave-particle duality was first proposed to explain the behavior of light. For centuries, scientists debated whether light was a wave or a stream of particles. In the 17th century, Isaac Newton proposed that light was composed of particles, which he called corpuscles. Around the same time, Christian Huygens suggested that light behaved as a wave. These two perspectives seemed mutually exclusive, and for many years, experiments appeared to support the wave theory. For example, Thomas Young's famous double-slit experiment in 1801 showed that when light passed through two slits, it created an interference pattern on a screen, a hallmark of wave behavior. However, the wave theory of light could not explain certain phenomena, such as the photoelectric effect, which was discovered in the late 19th century. In this effect, light striking a metal surface causes the emission of electrons from the surface. Classical wave theory predicted that increasing the intensity of the light would increase the energy of the emitted electrons, but experiments showed that only light of a certain frequency could cause electron emission, regardless of intensity. In 1905, Albert Einstein proposed a solution by suggesting that light could also behave as discrete packets of energy, called quanta or photons. This particle-like behavior of light explained the photoelectric effect, earning Einstein a Nobel Prize and marking the beginning of the modern understanding of wave-particle duality. Einstein's work on the photoelectric effect demonstrated that light, which had long been considered a wave, could also behave as a particle. But the duality of nature did not stop with light. In 1924, the French physicist Louis de Broglie extended the concept of wave-particle duality to matter. De Broglie proposed that particles, such as electrons, also exhibit wave-like properties. He hypothesized that the wavelength of any particle is inversely proportional to its momentum, a relationship described by the formula lambda equals h/p, where lambda is the wavelength, h is Planck's constant, and p is the momentum of the particle. This radical idea suggested that all matter, not just light, could behave as both waves and particles. De Broglie's hypothesis was confirmed experimentally in 1927 by Clinton Davison and Lester Germer, who observed the diffraction of electrons when they were scattered off a crystal. Diffraction is a behavior characteristic of waves, and their experiment provided direct evidence that electrons, which were traditionally thought of as particles, could exhibit wave-like behavior. This discovery was a major milestone in the development of quantum mechanics and established that wave-particle duality applied, not only to light but also to matter. Wave-particle duality implies that the nature of a quantum object depends on how it is observed. When scientists conduct experiments that measure wave-like properties, such as interference or diffraction, the object behaves as a wave. Conversely, when experiments are designed to detect particle-like properties, such as in the photoelectric effect or when measuring an electron's position, the object behaves as a particle. This duality is one of the most counterintuitive aspects of quantum mechanics, because it contradicts our everyday experience of the macroscopic world, where objects are either particles or waves but not both. One of the most famous demonstrations of wave-particle duality is the double-slit experiment. When a beam of light or a stream of particles such as electrons is directed at a barrier with two slits, an interference pattern forms on a screen behind the slits, as long as no attempt is made to observe through which slit the particles pass. This interference pattern is characteristic of wave behavior, suggesting that each particle passes through both slits simultaneously as a wave. However, if detectors are placed at the slits to observe the particles, the interference pattern disappears, and the particles behave like classical particles, passing through one slit or the other. This experiment illustrates that the act of measurement influences whether a quantum object behaves like a wave or a particle. The wave-particle duality is closely related to the concept of quantum superposition. In quantum mechanics, particles do not exist in a single, well-defined state until they are measured. Instead, they exist in a superposition of multiple states, and the act of measurement causes the system to collapse into one of the possible outcomes. In the context of wave-particle duality, this means that a quantum object can be thought of as being in a superposition of both wave and particle states, until an observation is made that forces it to behave like one or the other. Wave-particle duality has profound implications for our understanding of the nature of reality. It challenges the classical view that objects have well-defined properties independent of observation. Instead, the properties of quantum objects, such as whether they behave like waves or particles, are determined by the way they are measured. This has led to philosophical debates about the role of the observer in quantum mechanics and the nature of reality at the quantum level. In conclusion, wave-particle duality is a fundamental concept in quantum mechanics that describes how both light and matter can exhibit properties of both waves and particles depending on the experimental conditions. This duality has been confirmed through various experiments, such as the photoelectric effect, electron diffraction, and the double-slit experiment. The concept revolutionized physics by showing that the classical distinction between waves and particles does not hold at the quantum level. Wave-particle duality is a key element of the quantum world's strange and counterintuitive behavior, and it continues to inspire research into the nature of matter, energy, and the universe.